Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you all to the course of Advanced Computer Architecture. Before proceeding further, I would like to give you my brief introduction. My name is Muhammad Ashraf Chugtai. After completing my bachelor's degree from the University of Engineering and Technology, Lahore in 1974, and then I did my MSc from the same university in 1978. After this, I proceeded to UK for my PhD and completed my PhD program in 1986 from the University of Manchester Institute of Science and Technology. This way, after having spent 32 years at the University of Engineering and Technology, Lahore, starting my career as a lecturer and going up to the professor, I left the university in UET in 2006, and presently I am associated with the ComSet's Institute of Information Technology, Lahore. I have developed this course with an assumption that you have the basic knowledge of digital logic design, computer organization and design, programming models of microprocessor, memory systems, input-output interfacing with the microprocessor and coprocessors, fundamentals of computer architecture, computer systems, and similar basic knowledge. Now, we will give brief description of what is a computer system. A computer system is a collection of central processing unit, memory system, and peripheral devices. All the three components are interconnected by groups of conductors called buses. Now we will talk about the difference between computer architecture and computer organization. Computer architecture refers to those attributes of a computer which are visible to a programmer or to a compiler writer. For instance, the instruction set of a microprocessor, the addressing techniques which are being used, or the input-output mechanism, etc. Whereas the computer organization refers to a computer, how a computer is being implemented. For example, how the control signals are implemented or generated. Either these control signals are generated by using the concepts of finite state machine, or they are generated by using the concepts of microprogramming. Similarly, what type of memory system is being used. Whether the memory system used is a dynamic RAM or it is a static RAM. Similarly, the realization of operation is hardware or software based. For example, if we have to implement the multiplication algorithm, whether this multiplication unit is developed by using some hardware like combinational logic circuits, or it has been implemented algorithmically like by using the concepts of programming and repeated addition of the particular numbers. Furthermore, the members of a processor family, for example, say Intel 86 or IBM family, they share the basic architecture, whereas the organization of the same architecture may be different. For example, for different families, different versions of the Intel 86 microprocessor may be used in different types of organization. However, in this course, the word architecture covers all the three aspects of a computer design, that is the instruction set architecture, organization, and hardware. The development of computer design and its realization has got a long history of more than 6 decades. It has got both aspects of developments at the academic level and developments at the commercial level. At the academic level, it was back in 1944 when John von Neumann introduced the concepts of stored programming. In 1945 and 46, the word first operational computer was introduced. This first operational computer used 18,000 vacuum tubes, and it could perform 1900 instructions per second. This development continued, and then in 1946, another machine was introduced at the Princeton University known as ISA machines. This machine was 10 times faster than its predecessor ENIAC. This process continued, and at the same time, new developments started from the commercial point of view. From the commercial point of view, it was in 1949 when the first machine was introduced known as Universal Automatic Computer UNIAC 1, and however it was a very expensive machine. This machine was costing more than $1 million. This process at the commercial level gave rise to the trend of producing big machines like IBM, which introduced in 1952, machine IBM 701, and then the Control Data Corporation, which introduced supercomputers CDC 6600 in 1963. However, this trend continued developing bigger machines, but it was at the same time when in 1970 the concept of microprocessor was introduced. This was a new development, a very high value achievement when thousands of transistors in the beginning were integrated onto a single chip, and the size of a microprocessor was reduced from hundreds of square feet to only a few inches or a few square inches. As a result, by 2000, the mainframe, supercomputers, and mini supercomputers were replaced by massively parallel processors. At the same time, the mini computer, workstations, and PCs have been introduced. Primary aim of this course is to have an in-depth study of the computer architecture. The emphasis will be given to expose the advances in measuring the performance and making cost-performance analysis for the development of these computers. In this course, we will have emphasis onto 6 different areas. Number 1, the quantitative principles of computer design. Here, we will be talking about the impact of time and volume. That is, how by enhancing the speed of operation and how by enhancing the volume in the production of the computer components, we can reduce the cost and we can improve the performance. Then we will also talk about the measurement of different tools which are used to measure the performance of a microprocessor and the performance of a complete system. Then we will also be talking about the instruction set architecture. That is, what are the different classification of instruction sets? Or different types of instructions are used? What are different types of memory systems which are used in conjunction with different types of instruction set architectures? Then we will be also talking about how the design of a microprocessor changes while considering the floating point instructions and integer type instructions. So all these topics will be taken into consideration. Then we will move on to the discussion onto the design of the data path and control. However, I will assume that you have got the basic knowledge of what is a data path and what are different techniques which are used for the design of a control path. But while talking about the design concepts of the data path, we will give more emphasis onto the parallelism in the execution of the instruction. Talking about the parallelism in the instruction set architecture, our emphasis will be what happens to the design when we take into consideration the integer type instructions and the floating point instructions. How different types of hazards are introduced when we will talk about the instruction level parallelism, and then how we can remove these hazards. After having a detailed discussion, this will be our major area of discussion, and after this we will talk about the memory design. What are different types of memories which can be used? For example, the main memory of a computer, the cache, and the hard drives are the external memories. And then how all these different types of memory systems, they are integrated together, and we develop a complete hierarchy of the memory system. Having discussion onto the hierarchy of the memory system, we will be talking about the multiprocessor architecture. That is, how more than one microprocessors can be interconnected for massively large parallel computers or parallel processors. Then we will be moving on to the discussion onto the input-output devices, the storage devices, and how they affect the overall performance of the system. So our major emphasis in this course will be the performance-based analysis, the system development, and how the cost analysis or the cost also affects the overall design. Then at the end, we will be talking about the computer clusters, which deals with the interconnecting of more than two computers together, the routing problems in these interconnected computers, and how more than two, a large number of computers can be interconnected in the form of a cluster of computers. And then we will take into consideration different case studies, like the case studies for Gmail, what type of system is being used, different parallel processing concepts are integrated into the whole design of a big system. So this will be our major emphasis onto the computer design. Talking about after having a discussion onto all these things, in fact, we will be covering all aspects of the computer architecture, the computer design, and the integration of different components to have massively large machines. So this will be our basic emphasis onto different aspects of the computer architecture. Now I will give you a brief introduction about which textbooks we'll be using, what will be the reference books which we will be using, and then how we will be working during the execution of whole of this program. For the study of this course, the basic textbooks used will be the Computer Architecture, a Quantitative Approach, written by Hennessy and Peterson. We will be following basically the third edition, and to some extent, sometimes we will also be taking help from the latest edition, which is the fourth edition of this particular book. In order to give more emphasis and explain different hard topics of this particular course, we will be, in fact, taking help from other books, like the books being written by Hennessy and Peterson, the same author as we are using the textbook. We will be using his other book, that is the Computer Organization and Design. It's hardware and software interfacing. The second edition of this book will be quite useful in order to review all the previous concepts. At the same time, we will also be using the book written by William Starling, that is Computer Organization and Architecture. It's sixth edition, and if available, the seventh edition, may also be touching about this. However, during this course, we will also be getting help from the literature. we will be using the transactions on computer from IEEE or ACM. This way we will also be getting some help from the literature, and we will try to have deep discussion, and all the latest information will also be taken into consideration during this course. So with this much introduction about the course, now I would like to give you some introduction about the distribution of the course, that how different parts of the course will be covered with reference to your textbook. So from this point of view, basically your first chapter of the textbook, which is on the fundamentals of computer design, this will be mostly used to review your previous concept which you have already studied at your undergraduate level. And just after this, we will try to cover up the topics in 2 lectures. Then we will be talking about instruction set architectures of different types of microprocessors, their differences, different types of instruction word formats like 0 address format, 1 address format, 2 address format, and 3 address format. Next, we will be talking about the pipeline architecture. The pipeline basics are given in your book. This textbook in the appendix A, whereas it is the detailed information is also available in your reference books, that is the Computer Organization and Design by the same authors, Hennessy and Peterson. Then after having a review of the basic concepts of pipeline architecture, we will also introduce over here what are different types of hazards which may occur, and how these hazards can be removed or can be reduced by using the concepts of stalling and by using the concepts of forwarding. After making these small discussions and reviewing all these concepts, then we will talk about instruction level parallelism. This is covered in your book in 2 chapters, that is the chapter number 3 and chapter number 4. This basically describes what happens when more than one instructions are executed in parallel, like in pipeline architecture, and particularly when the instructions are mixed, like the integer type instructions and floating point instructions, they are mixed together. Definitely, as you know, that the floating point instructions usually take more time as compared to the integer instruction. So therefore, in order to take care of the hazards which may occur, we will be talking about how different events are being scheduled, and they can be, in fact, once they are scheduled, and then we can make different types of scoreboards, and we can find out or schedule these particular events, and then we can remove the hazards from the system. Then next we will be talking about the memory hierarchy, which is given in chapter 5 of your book. In this memory hierarchy, we will be talking about the cache memory design, the virtual memory system, and the integration of different types of memory systems at different levels, and then studying their performance. Then in chapter 7, where the storage devices, the input devices, and their impact onto the performance of the system, that is studied. The chapter 8 deals with the interconnection networks, where we will be talking about the clusters of computers and their performance. Different case studies will also be made in this chapter. In this whole program, I want you to succeed, but you need to show your intentions to succeed. How you can show your intentions to succeed and what will be my role in that, that depends. I think that I will be giving you some projects from time to time, and you have to show the performance in those projects, in the completion of those projects. The I think that I will be giving you the projects which may last for 3 to 4 weeks. And you may be allowed to work in the form of either as a single person, or if possible, you can have a group of 1 or 2. But in order to complete these projects, I will be assigning you some teaching associate. You may get some help from the teaching associate from the time to time. But in order to complete these projects, you will be required to do some research. The research will be done by going through and downloading the information from websites of different universities, as I mentioned in the reference section, the different journals like IEEE Transactions on Computers, the proceedings of different conferences at national and international level, and then covering different aspects of the course we will be talking about. So this is basically what will be our course style. I have given you a brief history of computers development, both at the academic level as well as at the commercial level. Then I have given you the introduction to the course, how we will be proceeding further. With this much introduction to the course and history of the computers, I think now we are in a position to start our discussion on to what is computer architecture, how we can look into computer architecture from different point of views, and how different parts of a computer are being designed, and their performance is evaluated at different levels of the design hierarchy. So I will start with, first I will give you the 4 basic perspectives of computer architecture. A computer architecture can be viewed from the processor design, memory hierarchy, input-output storage devices, multiprocessor and interconnection. These are 4 basic areas in which we can look into the design of a computer. So first of all, I will talk about what do we mean by, or what we are going to cover while talking about the processor design. The processor design basically deals with the design of instruction set architecture, then its implementation onto a VLSI chip, and then some embedded memory if it is possible, which is possible nowadays at this stage. However, at the instruction set level, we have to see what type of instructions are to be designed for taking into consideration the pipelining, how we can introduce instruction level parallelism at this stage, then how we will schedule our whole process in order to remove the hazards, and then we can also look into different architectures, that is like superscalar, reordering predictions, and speculations which might be possible in order to remove certain hazards over there. From the VLSI design point of view, we will look into how a VLSI chip is being designed, what are different steps which are taken. This will be just a small introduction about these things. Then we will also be talking about what type of internal fast memories can be introduced in order to enhance the performance of a system, and how they work, and what is their impact on the performance of a microprocessor. Having talked about the processor design, then the memory hierarchy. Memory hierarchy, in fact, deals with the organization of memory at different levels of the design. For example, the level 1 cache memory is usually placed inside the microprocessor chip, whereas level 2 cache memories are kept outside the microprocessor. However, at present in certain microprocessor architectures, people have started introducing level 2 cache also inside the microprocessor chip. Whereas the other level of the memory is the dynamic random access memory. How this memory is being designed, what are the attributes and what are basically the limits which in fact controls the performance of the dynamic memory and how it affects the performance of the microprocessor. Whereas in a complete system, then in the memory hierarchy, we have to take into consideration the role of external storage devices, their design from the point of view that they should appear to the microprocessor as if all the information is being contained in the main memory, but the basic information is actually physically available onto the secondary storage like hard disk. This concept is known as the virtual memory concept, whereby we discuss in detail and we see that how the memory system works at different levels of the design hierarchy. The third perspective of the system is the I/O devices, how these devices are interfaced with the microprocessor and with the other parts of the system. So this basically deals with what type of I/O devices are being used. For example, whether these are only the disk or tape memories which are to be used, or in addition to this, some additional devices may also have to be connected. What is the impact of these additional devices like printers, etc., onto the overall performance of the system? That is the main area of concern while talking about the design of the I/O systems. Then once we know, that is how the processor has been designed, how the memory has been developed and different parts in the memory hierarchy and their interconnections, then the I/O storage devices, then the most important part comes when we are interested in interfacing more than one processors together and designing a massive parallel processing system. For this purpose, different types of concepts are being implemented, such as the shared memory system, in which there is only one memory unit, but it is shared by more than one processors. However, the other architecture and then the other issues in this have to be taken into consideration. These issues deal with how coherency has to be established between different programs, how the memory is to be shared, and what is the impact of this memory sharing onto the performance of the system. So this is one way of looking into the computer architecture, where we consider a look into the computer architecture with four perspectives. That is the processor design, memory hierarchy, input-output storages, and the interconnection of these systems. So this is one way of looking into the microprocessor architecture. With this basic concept of what a computer looks like, what is a computer architecture, our major emphasis in today's discussion is onto the computer design cycle. Basically, computer design is a very complex issue. Here, we have to take into consideration three major factors. That is the performance, what type of performance we want to achieve, how we can get this performance. For this purpose, we have to look into what are the technology trends. Based on those technology trends, we have to find out what is the impact of the technology trends onto the cost of the system. As you can now see from this figure, which shows you the design cycle, you can see that the computer design is evaluated for bottlenecks using certain benchmarks to achieve the optimum performance. Here, what is our emphasis? Our emphasis is onto looking into the performance of the system. And while looking into the performance of the system, this means we have to have some basic standards based on which we should be capable of measuring the performance of the system. Those basic standards They are available in the form of some standard programs known as benchmarks. When we look into the performance, what type of bottlenecks may arise, and then while making the design, how we can improve upon these bottlenecks, and we can design the whole system according to give us the best possible performance. So first let us see, what do we mean by performance? Performance can be defined from different point of views. As a single desktop user, performance is defined in terms of the time or the latency of the computer. This time may be measured as the wall clock time. For example, how much time a laptop or a desktop user takes to execute a particular program. That is, in fact, the criteria for the measurement of a performance of a single user. Whereas when we have to talk about the performance from the point of view of a computer center administrator who has to execute number of jobs in a specified period of time. In this particular case, it is the overall throughput, that is, how many programs or how many users have been served during a specified period of time, which means the number of tasks, that is the measure of the performance. In case of single user, it is the time taken to execute a single program. Whereas in case of the computer center administrator, it is the measure of number of jobs which have been executed during a specific period of time. However, the other measures for the performance are what is the millions of instructions which can be executed by a computer program. So actually this concept of measuring the performance in terms of millions of instructions per second, which is known as a MIPS, it was introduced sometimes in the era of supercomputers, when people were interested in executing instructions, millions of instructions in 1 second. However, at the same time, the performance is also affected if the instructions are of different type. For example, if the instructions are floating point instructions, then they take usually more time as compared to the execution of an integer instruction. So for the measurement of floating point instructions, we usually define the units of M flops, that is million floating point instructions per second. Whereas the other measure is the clock frequency. That is also another measure for the performance measurement. So based on this, when we talk about the performance, we have to look into what are the performance measurement tools which are available. The performance measurement tools available are at different levels. Number one, it is benchmarks. Then some hardware tools may also be used for this purpose, which may be used to estimate the delay, what is the total area which is required to integrate a chip onto the silicon, and so on. And what is the power consumption? Power consumption is a very important thing, and it is a hardware-related thing. So we always, in order to enhance the performance, we are always interested in reducing the power consumption. Whereas the whole design is a very complex process. Therefore, we have to evaluate the performance of the design at different levels of design abstraction. The most important design is the instruction set architecture level. This requires basically simulation and then analyzing the performance of the system. The other is when we design a system at the hardware level, we simulate the system by using hardware, the register transfer language, and then we can analyze the performance. The other way of analyzing the performance is to analyze the performance during the design process at the gate level and then at the circuit level. So different levels, at different levels of design. I will talk about the levels of design abstraction in detail in this course. However, at this time, just to talk about what are different performance measurement tools which we can use. I'm just giving you a brief introduction about this. The other important thing while measuring the performance of the input-output devices is how the data or the information can be transferred from a source to the input or to the output device. And during this transfer, we have to place them in a buffer so that on the completion of the execution of one instruction, the next instruction or next set of instructions may be taken up. This process is known as the queuing process, and for this purpose, queuing theory is, the concepts of the queuing theory are used. Those of you who are familiar with the mathematical analysis of certain things, they are well familiar with the queuing theory also. Whereas in other way of measuring the performance is to use certain rules of thumb, which means that we know this thing that it is always better to have minimum performance. So that is one rule of thumb, that in the design, the power should be minimum. The other is the time to execute instructions should be minimum. Number of components on the chip should be minimum, and so on and so forth. So therefore, while making use of the measurement of performance, we also use certain laws and certain principles, in which we will also be talking about this also in details in the third lecture, I think most probably, that there are certain rules which we have to follow in order to enhance the performance. So this is one first step, that is design a system based on the performance. However, as I mentioned earlier in the beginning of this particular introduction, that performance is very much affected by the technology. As you can see from this slide, that the technology basically deals with how or what type of new designs are necessary. These designs are simulated to evaluate the performance for different levels of workload. This simulation helps in keeping the result verification. Whereas the technology trends, they are very, very important. These technology trends have given rise to the enhancement in the performance, as well as it has affected the overall cost of the system. So based on the technology trends, we can define different generations of computers. Usually, the generation of computers started in early 40s to mid 50s, where the vacuum tubes were used. I think most of you might have not seen the vacuum tubes, but a vacuum tube in its bigger form is your television picture tube, which is the monitor. It is in a bigger form, whereas a vacuum tube is relatively a very small device as compared to this, but not small as compared to a transistor. It is approximately 100 times bigger than a transistor. But at that time, it was the small device of about 1 inch diameter and 4 to 5 inch length. This tube has got certain electrodes with the help of which we can control the flow of current, and these devices can be used as switches in order to implement concepts of the switching theory. These were the first generation computers. In the second generation, which is the era between 1958 to 64, silicon transistors were introduced. These are silicon as well as germanium transistors were introduced, which is as compared to a tube, it is 1/100th time smaller device. It has got, as you are, I think that you are familiar with this, it has got 3 legs, and one is known as the early versions such as the bipolar junction transistor. They have three legs known as the base, emitter, and collector. And base is used to control the flow of current through this device, and this device can be used as a switch also. This, in fact, drastically reduced the size of a microprocessor as well as all other its peripheral devices. Then its size was further reduced in 1965 up to 1968. During this time, the efforts were made to integrate more than one transistor onto a single chip. This concept is known as an integrated circuit design chip. This, in fact, gave rise to the third generation computers because by integrating the transistors onto a single chip, a lot of performance enhancement became possible because this reduced the propagation delay of the signal from one transistor to another transistor, which was initially it was connected by using solid wires. Then all these wires were also made onto the integrated circuit chip. The propagation delay was reduced, the power consumption was reduced, and the size was reduced. So ultimately, the performance, we can say, was enhanced from all aspects. At the same time, it became possible to reduce the cost of the system. Then during the time of 1972 to 77, further developments became possible, and the technology, in fact, moved from medium-scale integration. First it was small-scale integration, then medium-scale integration, and then it was moved to the large-scale integration known as LSA circuits. At this time, more than 100,000 transistors were integrated onto a single chip. This concept was further enhanced, and during 1978 and onwards, the concept of very large-scale integrated circuits, that is VLSI, that was introduced, and this concept made possible the integration of about millions of transistors onto one chip. Whereas this is in fact the fourth generation of the computer development, or of the electronic circuit development. However, at present this has moved to ULSI, which is the ultra large scale integration, where over 100 millions of transistors can be integrated onto a single chip. So this way, these developments have been taking place from time to time, and this trend in fact gave rise to the enhancement in the design, enhancement in the performance, and reduction in the cost of a processor. So with this much introduction, now you can see that from this slide it will become clear to you that how this trend in fact helped us in increasing the density of the computer and then reducing the number of components. This graph shows basically the technology trends, and it shows that how the number of transistors have been increasing with the passage of time. So basically all this is governed by the Professor Gordon Moore's law, which stated in early 60s that density of transistors onto an integrated circuit will double, or it will be increased at the rate of 1.8 to 1.9 times every year. And it is the result of this that today it has become possible to have millions of transistors onto a chip. However, its impact on the performance of the processor, you can see this thing from this second next slide, where you can see that in 1965, when mini computers were having the performance, whatsoever was the performance of the mini computers in 1965, that is in fact the performance of a microprocessor in 1985. And similarly, the performance of a supercomputer introduced in 1970 is now possible since 1985 by massively interconnected or parallel microprocessors. The third parameter in the design cycle is the cost. This is the most important parameter. It was the cost, due to which it is the reduction in the cost, due to which today we are in a position to get a very high performance computer available in the form of a desktop computer or a laptop computer. Otherwise, the same computer which was available in 1960 at the cost of $1 million, today it is available only at the cost of a few thousands of rupees, not dollars. That was $1 million, whereas today its cost is in thousands of rupees or in hundreds of dollars. It has become possible due to the latest technology. However, when we talk about cost and the price, these are two different components which we must have to take into consideration, and they must be identified very clearly. Cost is in fact the total cost of the production. It includes the cost of the design. For example, one microprocessor chip design of medium-size complexity may cost you about $200 to $300 million. This is a very high cost, but we can reduce the price. Price is the selling price, where selling price depends upon the volume. So now if we produce 200 million processors, and we are in a position to sell these 200 million processors, the overall design cost of one processor will reduce to $1 only. But if the market is, if its price is not reduced, then this means we will not be able to get high market, and based on this, it will become useless to have microprocessors of very high performance, but at a very high cost also, or a selling price also. Therefore, it has always been necessary to reduce the selling price of a particular design. So with this much introduction about what is a design cycle, I will summarize this today's discussion by saying that in the beginning I gave you a brief introduction to the developments in computer technology, and then we talked about the design perspectives and the design cycle. Next time, inshallah, we will be talking about the next steps which are to be taken for design of a microprocessor in further details. Okay, at this stage, I will stop. I say thank you, all of you, for listening me, and Assalamu alaikum.